Thank you very
much. So, and thank you for inviting me here. It's a great meeting here, and I think indeed the connection will become clear as I speak. Since while now we have to take maybe 2 steps back from the previous 2 talks, that at the end I will try to convince you that our platform, or rather even in more general, the idea has a strong connection to making the collective measurements, such as the conversion between the Hadamard words and PDM. So I come from an experimental group, so I will start by introducing our experimental platform, which is a multifunctional quantum memory. So our memory is based on an atomic ensemble where photon can be stored as so-called spin waves, which are the collective excitations of many atoms. However, that's not the only feature, because the memory can also emit spontaneous photons. Therefore, it may serve as a photon generator or even a single or multi-photon generator. But the truly new feature of our platform is that we can interfere the stored photons inside the memory. We can interfere them between different types of modes. So in general, I would say there are two spaces here. One is the time frequency space. So the memory can be spectrally or temporally multiplexed, and the wave vector spatial space, so x, kx, where the photons can reside in different parts of the memory or have different spatial coherence. Then we can think of applications such as the important quantum repeaters that have been also the topic of this meeting, that can now be multi-mode. But if we can process the information inside the memory, then perhaps we can implement the error correction, which I will mention briefly, and even make some quantum gates, especially since with some newer ideas, the atoms can also be made to interact. And the system, at least at the moment, is actually an atomic ensemble of rubidium-87 atoms, somewhere at the temperature where it is not a Bose-Einstein condensate, but it is just a thermal cloud that, via a low temperature, allows long storage of spatial coherences. So it just don't diffuse immediately like it would happen at room temperature. Originally, we have demonstrated this platform as a generator of many photons in many different wave vector modes, but today's topic will rather rely on a slightly different feature of this memory. Nevertheless, the common feature is the protocol, where we first can store a signal in this very popular lambda scheme by applying a control field. Then it is stored in the form of spin waves, and then at the end it can maybe retrieved using the same or similar control field. And in particular, if you look classically at the picture of the atomic coherence in the ground state, and the spin wave may be understood as the wave that appears in the off-diagonal element. What is important for today's topic is the idea that came around 2009, that you can place such a atomic cloud in or an atomic ensemble, hot atoms in the original proposal, in a gradient of magnetic field, and then different frequencies of light may be stored at different positions of the atomic ensemble, simply by the fact that during storage there is a detuning with respect made by the Zeeman shift. So if now we are storing different frequencies at different positions, that also means that we are storing different times at the different wave vectors, just because of the correspondence of the Fourier transform. So T omega and Z, where the gradient is, versus the longitudinal wave vector Kz. So if we do that, then we may understand that only light that has a kz of 0 is only the spin waves that have a phase of 0, so kz equal to 0, may be read out or absorbed into the memory. Therefore, we may understand it as a kind of a photon echo. So now, for example, we can store, we may keep applying the gradient and store several pulses. And then if we flip the gradient, then actually the kz is reversed, and we may retrieve an arbitrary pulse, actually in an arbitrary order, assuming that we can switch this magnetic field. However, the magnetic field has some disadvantages. It cannot be switched too rapidly. Therefore, we have developed another idea where we use a strong off-resonant laser, which induces an AC Stark shift instead of the Zeeman shift to achieve pretty much the same. However, it can also achieve more because it may be shaped using a spatial light modulator. So, for example, if we apply a periodic modulation along the Z direction or any direction really, then the spin waves will be diffracted as if they impinge on a diffraction grating. So we increase the power of the modulation, and then the spin waves that started in ky in this case equals 0 get diffracted into subsequent diffraction orders. So in this way, we may also implement a beam splitter if we just park at the proper modulation power. Then the spin waves will be split equally between 0th and 1st orders. So it's like as if they impinge on a diffraction grating. Some of them are unfortunately lost, so that's not a 100% efficient process. But nevertheless, we may, for example, make a lossy beam splitter for 2 modes. So we have observed that, and since everything is happening inside the quantum memory, then the visibility of such interference is actually pretty high, more than 95%, and even 98, 99% in our recent demonstrations. So as one of our first demonstrations, we have actually prepared 2 Fock state spin waves, so just the 1-1 state, and interfered them using this technique and observed the Hongu-Mandel interference. So that actually is the simplest quantum operation in linear optical quantum information processing. So we have shown that we can do that, and actually the visibility and efficiency of that was mostly limited by the quality of prepared photons, not necessarily by the interference. So the subsequent application, again, we can also interfere in the Z domain. So as I have shown before, we could store pulses at different times and retrieve them in a different order, but we can also store a pulse, make it diffract on this AC Stark grating, store another light pulse, and then apply a grating with half of the modulation depth, which will make everything interfere. So now at 0, we have the first and second with a plus. We may retrieve it, and then we apply the grating again, and then we have actually the other part of this beam splitter. So that means that we can now store pulses in the memory and then retrieve them after a beam splitter operation. So before I actually come to the next topic, I want to say that this is a platform, a programmable platform to interfere those spin waves, which are actually just stored photons. Now, our most recent work has brought this technique to the quite complex level, where we have remembered the topic that's been very much touched upon yesterday. So the interference-based way of beating the Rayleigh limit. And interestingly, while everybody or almost everybody now is trying to beat the Rayleigh limit in imaging, actually Rayleigh originally considered it in the case of spectroscopy. So we come back to this problem. And as you have heard already yesterday, the separation between such two incoherent sources cannot be estimated if they are too close using direct imaging, because the two, let's say, Gaussians will just blur together. However, if you look at the ultimate bound, then it says that actually you should be able to do it. And indeed, many techniques allow that in imaging. And one of them in particular splits the source into two paths of an interferometer, inverts one of the images and interferes them again, which makes a projection onto just the right mode. So the mode that contains this theta, which here is the information about separation of the two sources. So now we design the protocol. We use our spectrum to space mapping to be able to put phases onto different coherences. And we also use the so-called technique of time lensing, where we just chirp the control field such that the frequencies are split. So that, let's say that this is a technicality. In any case, our memory allows us to implement a quadratic spectral dispersion. So something that is very common in optical fibers, but in the nanometer range. And here we can programmatically apply a spectral phase in the range with the resolution of 20 kilohertz or so. So if we just do that, so like we make a simple spectro-temporal lens, then we may make a Fourier transform as a normal lens makes a Fourier transform. So if we, for example, enter with two pulses, then we get a comp at the output, or if we enter with a comp, then we get two pulses at the output. So we can make a Fourier transform of the signal. So that's like a classical spectroscopy. It's just like putting a diffraction grating on the lens. So if we do that with two incoherent sources, then they are very much blurred. And for small separations, they are completely indistinguishable. So we go to our interferometric techniques, and we get the idea that actually when you invert the gradient, then you are also inverting the time axis. So the natural order where you come in with positive gradient in the memory and come out with a negative gradient gives you the reversal of the temporal order of the pulses that enter the memory. So it's natural to implement something like the sliver protocol in this memory. So with that idea, we designed a protocol that pretty much uses this these gratings of various kinds and temporal modulation, such that now the two input incoherent pulses are sorted into the plus and minus combinations, which leave the memory at different moments. So now we have the very strong sensitivity to the separation. It may be understood in the phase space picture. For that, I will have to recommend our very recently published paper on that. And the phase space picture allows us to understand how to make those transformations such that we can single out the specific or project onto a specific combination of modes. And with that technique, we can see that with the blue curve here is the direct imaging approach implemented with this time lenses, and the advanced interferometric approach can beat this approach quite substantially for small separations indeed. And as is known in the field, for even smaller separations, we still go to zero. So the ultimate bound is never reached because it's only reached for 100% visibility and no noise. That's a rather fundamental result. So where can we apply this technique? we're thinking of obviously other atomic systems where we need to separate some too close by spectral lines that come maybe from single ions, that come maybe from different atomic ensembles sitting in different magnetic fields, or systems which naturally also have very small, very high quality factors which have narrowband lines, such as optomechanical membranes, studied very intensively nowadays. So the pretty much only approach that's been taken to this super resolution spectroscopy so far has been the quantum passgate that I believe you have heard about on Friday as well. But it has maybe a similar performance, but it operates in a vastly different spectral domain in terms of resolution sigma that we have here, and I think we demonstrated that this memory can really program. We can program it to for such interesting protocols. So finally, I promise that I will come back to the joint detection. So now I'm not gonna explain exactly how, but by programming the memory differently, we can indeed decode the Hadamard words. So that's actually something that we have done even before many optimizations that were required for the previous paper. So you can see the result is actually quite horrible, I think. The photons are really just leaking into the non-existing time bins, and the visibility is maybe 70% here. So many improvements are needed, but in fact, I think the approach of us being able to program the device to realize very different protocols is excellent for working with community that has many ideas for new protocols. Because we don't need to build a new setup every time there is a nice idea. So I also believe that this is maybe not the platform for the ultimate solution. There are different platforms that work in different spectral domains. For example, electro-optic modulators and grating, or volume holographic grating spectral shapers, or the quantum memories based on crystals that have rather gigahertz than megahertz bandwidth compared to ours. But as we discussed more broadly in the article, those platforms can implement our protocol and many of the methods that we propose. So thank you for your attention, and yeah, I'm be ready to answer some of the questions.
Yeah, first of thanks. So, our first question is always, what do you think will be the main use case for entanglement-assisted communication use cases, the first main
So I will start with the challenge, if you don't mind. I think sure. the challenge that I can help with is making the entanglement transmission very multiplexed and multimode, or maybe even the looking at the high dimensional entanglement. So in some of our works, we have shown that the memory can process that kind of entanglement, so it can be a quantum repeater for many modes. But of course, the transmission then also becomes more difficult. So I think we know that the classical networks, the high capacity networks, use wavelength division, multiplexing, and pretty much many fibers. So that's really required to get any rate. So I think the multiplexing is an important challenge, and the application perhaps in the far future, I'm most fascinated about connecting different quantum processing machines. I don't want to say computers, because it's like a computer must be like a general purpose thing, while, for example, the memory like that can make some operations, and that can be very useful.
And do you see any chance there is going to be a contribution, a technological one, to 6G from that domain?
So of course, as many have mentioned, that's not yet clear what 6G will be, but I think we can understand that it will require using high frequency optical fields, more than a terahertz, probably. So maybe here I will say something unusual. Our atomic ensemble, with our atomic ensembles, we are working on making on using Rydberg atoms. So we excite the atoms to the Rydberg states, and we want to map such fields. So that could be used. So that's a kind of a quantum technology. It doesn't use entanglement, but we are working on mapping such fields in the near field, close to the antennas, close to the receivers, that could be used in 6G. So it's very hard to detect those fields. It's very hard to map them. So I actually hope that the Rydberg atoms do provide a unique opportunity here for diagnostics of such devices.
Great. Then let's thank you again here. And all the speakers of this session could please come to the first row so that we can have a discussion on the topic.